Now, the reason why we should care whether or not a tropical storm is electrical and whether the hot towers and the lightning that occurs right before rapid intensification is a effect of rather than a cause to that storm's rapid intensification, it drives right into the climate change debate. And specifically, CO2 is the most interesting electrical element in clouds. And that's because pure water is highly insulative. And as you add atmospheric CO2 to it, pure water becomes between 4 to 10 times more conductive. On top of that, very specific to the location of a tropical storm, the low pressure in the winds take carbon dioxide that's dissolved in the ocean and put it into the location of the storm. It's very much like taking a beer and shaking it and cracking it open, and the change in the pressure from inside of what the can is contained to then being exposed to the atmosphere causes the CO2 to bubble out of the beer. Well, the same thing happens in the atmosphere, and it's very important because the conductivity is proportional to the amount of CO2 in the atmosphere. So you have a direct relationship. It's proportional. Now, more specifically, what you have inside cloud droplets is, and this is a very simple drawing here, what it shows is if this is a droplet and you have a negative set of charges on this side, then the opposite charge will attract, or if you have a magnetic field that's attracting positive charges, the movement inside of the droplet of those charges is going to depend on the conductivity of the droplet. And where that becomes really cool in a tropical storm is not on a small scale where the droplet is. I mean, it's important. You go kind of from microphysics to clouds and convection. But you just first have you first start out with the idea that in convection you have water molecules coming together and forming these droplets, and it's pure water. And then you have the atmospheric CO2 coming in, making it more conductive. And then you have it in the context of a cloud, and not small scale, but very, very large scale electrical conditions and potential differences. And so if you have in the hot tower a lightning strike going down, that big hot tower, which gets up to 20,000 feet into the atmosphere, getting closer and closer to the ionosphere, the conductive part of the atmosphere, and you have these clouds where electrical conditions then go to the outside of the droplet and then collectively to the outside of the cloud. There's this joke about every cloud has a silver lining, but every cloud on the outside, if it has a collection of charges that are appearing, it's very interesting electrically because water it has a high dielectric constant, and what that means is a magnetic field cannot travel through it very well. And so if you have these magnetic fields that are on the outside of a cloud, what it means is the electric field isn't going to really be very interesting inside the cloud, but on the outside of it, its field potential can be translated to its surroundings, again on the outside of a cloud. And so you have these lightning strikes that are creating these momentary huge potential differences, and then kind of a buffering of it, and then eventually the field effect local to the strike goes away, and then eventually you're left with this permanent potential difference between the upper part of the atmosphere and the ground. Now, tropical storms are structurally unique in terms of their pressures. What you have with a tropical storm typically is a low pressure at the surface, and then a high pressure aloft. And then as convection occurs, it causes the air to expand, become warmer, therefore lighter than the surrounding air, for it to rise, and then as it gets to the higher part of the storm, you get high pressure and what's known as subsidence, where kind of the opposite effect is occurring. And what's interesting again about this is if you have a potential difference where you have electrically positive charges in the upper atmosphere and the negative charges on the ocean surface, then this difference is going to kind of create a force, a static field force on the ions in the upper atmosphere. Those ions are then going to press down on the high pressure part of the storm and actually add to its organization. This is very, very significant because the big thing that gets these tropical storms and whether or not they form is whether or not they get sheared, or upper level winds disconnect the high pressure with the low pressure and doesn't allow the tropical storm to breathe.